So in this video we are going to solve 1D linear convection equation which is given as dou u by dou t is equal to c dou u by dou x. It is called 1D because it has contained only one special variable and it is x. Now in order to solve any partial differential equation we need to use the technique called discretization of the domain. Now for discretization we are using forward differencing method for the time and the backward differencing method for the space. Now, by discretization, we can reduce the equation in the following form: ux t plus delta t. What is the meaning of ux t plus delta t? It is the value of u at x position at time t plus delta t. Now, by simplification, we can get the value of ux plus t plus delta t is equal to u of h at t and plus c, where c is a linear convection velocity or linear convection coefficient. Now, in order to fit this equation into Python, we are using the index I for x and index j for time. Now, if we are using that index, the equation is reduced to the following form. Now, we are going to import two library. One is numpy and another one is matplotlib.pyplot_plt. Now let me check it to the code. So now in order to discretize the domain we have to use the spacing between x. Now x is the 0.25, that is the meaning that grid spacing between two consecutive values of x is 0.25 and k is the grid spacing between two consecutive value of time, or you can call it as time steps also. Now let me execute this. Now h and k are set to be 0.25 and now we have to define our computational domain. So our computational domain is made of one is x-axis and another is t-axis. Now let it construct it in the Python. H equal to np dot arrange 0 comma we want our values up to h equal to 1.5, so 1.5 and with the spacing of h, and t is equal to np dot arrange with the starting from 0 to we want our value up to 2, so 2. Okay, now let it execute. Now let's print x. Now you can see that x is 0, 0.25. It is printing up to 1.25 only. So we need to use 1.5 plus h. So it is the property of arrange function that it is not counting the value given at the last. So now let's print x 0 to 1.5. It is printing correctly now, and 0 to 2, that is in the domain 0 to 2, so it is right. Now we have defined our computational domain. Now it's time to define our number of nodes. Number of nodes meaning the intersection of x and t line in the computational domain. So how can we define that? So in order to define that we need to calculate the length of x array. So length of x array means the number of element in the x. So how can we do that? So let's do n is make a variable called n is equal to len of x and make variable m is equal to len of t. Now let's run it now and print n. So n is equal to 7. Now let's see in our computational domain h 1, 2, 3, 4, 5, 6 and 7. So it is printing correctly. Now let's print m and it is saying that it is 9, 1, 2, 3, 4, 7, 8, 9. Now let's construct our U matrix from that value np dot jd ros n comma m. So it will construct the U matrix with n rows and m columns. Let's see. So now you can compare that at each and every point in this matrix assign the value of 0. So at every point the value of u is 0. Now in order to solve the partial differential equation we need to have two conditions. One is boundary condition. So let us define boundary condition. Now what do we mean by boundary? So we have to provide the boundaries as some values. So let's define these boundaries, the dots showing in the domain. So you see that there are 1, 2, 3, 4, 5. So for every row and for the first column. So how can we define that? So u index for every row and first column, that means 0, is equal to 0. Now let's define the second boundary. Second boundary is given as for every row, like this is the row, one row, second, third, fourth. So for every row and for the last column the value is 0. So it's given as for every row and anything in the list last we can denote is as -1 is equal to 0. So we have defined our boundary condition properly. Now let's define our initial condition. Initial condition is in the computational domain, like this is our time. So initial condition is the condition of the velocity at t equal to 0. So it is matter of defining the last row. So let's define it. U of the first row means 0. Sorry, it's not the last, it's the first row from the down. So it's 0 means the first row, comma, and for the every column we have to define the values. So for every column equal to 0. Now let's print our velocity profile here. Plt dot plot. Now what do we want to print? X comma u. Now we want to print only the value of the spatial coordinates, all the spatial coordinate for the 0th time step. So it is like this. Now this velocity profile does not look correct, so let's change the setting here. Let's make it 2 is to 3. Now it will convert the value of x between node 2 and 3 to 0.2. Now let's run it. So you can see that our profile is coming. Now let's solve the equation with using discretization technique. This is our defining the problem first. Now we are going to solve the values of u at various time steps. Now for that we need to look at our computational domain first. So we need to calculate every values of x at every time step. So first it will go through every values of x. So our inner loop will be the loop for the spatial coordinates, and our outer loop is loop for the time coordinates. So first it will go through inner loop, that means it will calculate all the values of x. Now it will go to the next time step and it will calculate all the values of t equal to 0.5. So let's define our two loops. For j index is for our time index in range of, we don't know, let's define first. For I in range of, we will define it later. Now let's write the equation first. Now here our dt and dx is, dt is our time spacing and dx is our spacing in h direction, which is h multiplied by, now the number of times, how many times the loop will run, it we have to define it correctly, so that's why. Now let's look at our domain. We have defined our boundary condition first, so our I will go from 1 to 1 2 3 4 and 5, because our last boundary condition are known, so it is going from 1 to 5 only. So let's define it 1 to 5, but let's check what it will print for I in range 1 comma 5 t I. Sorry, print I. So 1 2 3 and 4, but we need 1 2 3 4 and 5, we need 5 as well, so let's define it to 6. And for j, we know the value of initial condition made that t equal to 0. Now we need to go j 1 2 3 4 5 6 7 and 8, so 1 to 8 we are going to need j 1 to 8. So let's check 1 to 9. Yeah, correct, it is showing 1 to 9. So it will calculate all the values of u at each time steps. Now C is not defined, so let's define our C first. C is the linear convection velocity 0.1. Now it is showing that index is out of bound. So why 9 is showing out of bound? Because if I put 9 here, that my j plus 1 will be 10, so that's why the j index should go only up to 9, so I have to write 8 here. Now it has done the calculation. Now let's plot, okay, our result blt dot plot. We need to h, it is u. I need all the rows and j column. I have to put this here into upper one because I want to plot for every j. Now before it plot, just clear all the figures from above plt dot clf. It will clear the figure at each and every iteration. Now let's show our plot. So our plot will be look like this. Now it is not showing the animation, but I have write the similar program in the PyCharm. Now look at this animation. I did not do anything Extra here I have just provided the X label, Y label and the title. So let's look at the output. It will come in the beautiful animated way. Just run it one more time like this.